Hong Kong, welcome to a series of virtual academic seminars to celebrate the launch of SmartMat. SmartMat is an open access journal co-launched by Wiley and Tianjin University. I'm one of the co-editors-in-chief. The other one is Professor Wenping Hu from Tianjin University. Today, Professor Andrea Kiss is a speaker. Before his talk, let me briefly introduce him. Andrea Kiss is an associate professor in electrical engineering at EPFL Lausanne. He started his group in 2008 and has made fundamental contributions to the study of the electronic properties of 2D materials and atomically thin TMDC, transition metal dichalcogenides. His pioneer work on moly-disulfide transistors was the first demonstration of high-quality device on a 2D semiconductor and has been cited over 10,000 times. He is a highly cited researcher and has received many awards. Now he is the editor-in-chief of the Nature partner journal 2D Materials and Applications. Before joining EPFL as faculty, he was a postdoc at UC Berkeley in the group of Alex Exciton. He received his PhD in physics from EPFL in 2003 and received his master's degree in physics from University of Zagreb, Croatia. Today, he's going to talk about excitonic device thesis on 2D semiconductor heterostructures. Let's welcome Andrea to give a talk. Andrea, please.
Thank you very much. Thank you very much for the introduction. I hope you can all hear me and see me. I'm just going which is one of the two Swiss Federal Institutes of Technologies. The other one is in Zurich. So this is the map of Switzerland. We're on the shores of Lake Geneva, on the outskirts of Lausanne. So that is the view of our campus. We also have now a couple of satellite campuses in other cities around Switzerland, but this is our main campus, the main center of gravity. And the university is focused on technical studies, so no literature or medicine and these kind of subjects. Now, in my group, which I have been running since 2008, we're working on several types of topics which are related to the science and engineering with 2D semiconductors, and we work on in a vertically integrated way. So these different topics, they interact with each other and draw in each other's strengths. So the first one is we started off first with these so-called classical semiconductor devices, where we looked at transistor and similar mainstream, let's say, semiconducting devices, but implemented with 2D materials, and we looked at issues like mobility, current density, and performance. Then we started off on realizing new device concepts, which are enabled by unique physics of 2D materials. This is what I will be mostly talking about today. And all of these topics are very strongly supported by our efforts in material growth, where we are growing a large number of transition metal dichalcogenides using CVD, MOCVD, also MD. And these materials are of very high quality, but they're also important to sort of support these other research activities in the group. So we're pretty much able to do all of this inside my group, work with all these different topics. Now, when I talk about 2D semiconductors and 2D materials, then I'm mostly referring to transition metal dichalcogenides. This is where I started off, and this is the class of materials that I'm still working with. So 2D transition metal dichalcogenides have this characteristic structure where you have 2D layers in which transition metals, so these metals are very strongly bound covalently with these chalcogen atoms, and these 2D sheets are stacked in a vertical direction, forming bulk crystals. And these single sheets can then be extracted from bulk crystals, and you can use them as building blocks for making mesoscopic devices of different kinds. Now, this family of materials is very interesting. And what attracted me to it in the beginning was the fact that using the same structure, same basic structure, you have on the order of around 40 stable materials. And depending on the metals and the chalcogens, you can cover a broad range of electrical properties. So you can have semiconductors, semi-metals, metals, and superconductors, depending on which metal enters the basic property. And then depending on the chalcogen atom, you modulate these basic properties, for example, the size of the band gap or the transition temperature of the superconductor. So you have here a very broad already playing field of different materials that you can work with. Now the 2D materials in general are a very rich and very rapidly moving research field. So we know of more than 500, maybe even in the thousands of potentially interesting 2D materials. So in addition to transition metal dichalcogenides, and of course also the other examples like boron nitride and graphene, we also have transition metal dichalcogenides, we have black phosphorus, transition metal dihalides, oxides, etc. So all of these form a very, very rich playground. And in this playground of different 2D materials, you have pretty much reflected the entire material science. You have metals, you have semiconductors, superconductors, piezoelectrics, magnets. And now the question is, well, if you can find all these examples of behavior also in bulk 3D materials, why is it interesting to look at them in the case of 2D materials? The reason for this is that 2D materials, because of their small atomic scale thickness, they allow you to change all these basic properties very, very easily. So you can start off with, for example, a 2D semiconductor that has a certain band gap, and then by changing the thickness, you change very easily the band gap. Or you can easily induce doping or magnetism by replacing or atoms or chemically functionalizing the surface. And all these 2D materials can also be strained to very large amounts of strain. So that is another tuning knob that you can use to modulate the properties. And of course, you can also use things like magnetic fields, electric fields, gating, and 2D materials, since they are all pretty much composed of surface atoms, they're all much, much more responsive to this kind of tuning. And in that sense, 2D materials are more relaxed, because if you look at a 3D semiconductor, like for example silicon, you know what its band gap. In the 2D form, all the materials, their starting properties are determined, but then they can very easily be changed, modified, turned into something else. So this freedom gives you a lot of possibilities for introducing different types of functionalities and properties. And one recent example for such wide tunabilities is a work that also came from my group. So one material that we looked at recently is platinum selenide that has this kind of a structure, and it covers a very broad range of tuning properties, because in bulk form it is a semi-metal or a metal. Once you thin it down to a single layer, it becomes a semiconductor. So it has a broad range of electrical tunability. But then in parallel with this tunability from a single layer semiconductor to a bulk metal, you can also induce magnetism in this material. And you can have a situation where the bulk material is non-magnetic, but then whenever you change the thickness, with the thickness lower than 10 nanometers, whenever you change the thickness by one layer, you can switch the magnetic behavior from antiferromagnetic to ferromagnetic behavior. And the single layer is actually recently showed an antiferromagnet. So this magnetic tunability is going in parallel with the electrical tunability, and it just makes this material very, very rich in this sense of different types of properties. And many other 2D materials are like that. They can change radically their behavior by just changing the number of layers in a small thin crystals. What was our main contribution to the field in the beginning was that back in 2010, and this was published in 2011, we showed that we can make a transistor using a single layer of molybdenum disulfide. And this was an important contribution because in those days, most of the research, well, pretty much all the research on 2D materials was focused on graphene and making devices with graphene. Now, the problem with graphene is that even though it has a lot of interesting physical properties, it doesn't have a band gap. So you cannot really use it that easily to make standard semiconducting devices, logic circuits, and pretty much everything that we're used to working with in electronics, because for that you need a band gap. So MOS2 was the first example of 2D material with a band gap, a 2D semiconductor, and we showed that we actually made the first working transistor based on this material, and we showed very high on-off ratio of 100 million, very good switching slope, and the more important thing about this result was that it basically showed that there are other materials that people knew of, but were not really studying, that can be used to make devices and can be used to study, and not just graphene and boron nitride as the substrate. So today, it's pretty much accepted that 2D materials could have interesting applications in semiconductor technology. So this was a perspective paper that was published last year in Nature, where some giants in the field of electronics, both in academia and in industry, they were very positive about the prospects of 2D materials and semiconductors in the context of extending Moore's law and the scaling of semiconductors. And here they also defined what are some of the main problems that have to be solved. And the first problem is that, well, simply since you have 500 or maybe thousands of materials to choose from, it would be good to have some kind of reliable modeling so that the choices could be narrowed down a little bit more before people start synthesizing and making experiments with them. The second is that we need to have good methods for producing these materials reliably on large scale so that we can make chips and integrated devices. And then finally, the problem is that since we have a lot of different research groups measuring things in similar but still somewhat different ways, there is some kind of a need for standardizing tests and results so that once we report on a property of a material, we are pretty much talking about the same things. So some of these subjects we're working on also in the group, especially the related to growth and synthesis. And here in synthesis, what we have lately been working on is MOCVD growth. So growth using metal organic chemical vapor deposition, where the idea is that we use precursors for growth of 2D materials, which are delivered in the gas phase. So for example, if you would like to grow MOS2, molybdenum disulfide, then the idea is that you deliver into a reactor a stream of argon gas, which carries in it vapors of molybdenum carbonyl. So that acts as a source of molybdenum. And then for sulfur, you can use H2S gas. And these react close to the surface, and you end up with growing large films of 2D material. So this we can grow on a wafer scale, molybdenum disulfide. For example, here are some examples of also molybdenum disulfide, tungsten disulfide, which have been grown with a large grain size on the order of even up to 1 millimeter in the case of tungsten disulfide. And this is probably, in my opinion, the most promising approach for going through the materials on an industrial scale. First off, because that's also the approach which is used for many other compound semiconductors. So the machinery is already, and the equipment is already mostly there. And also what is the advantage of this technique is that it very easily allows you to do doping, make heterostructures, etc., and you don't run out of materials like in the case of powder-based CVD growth. So one example where we recently used this material was in this paper we just published in Nature a couple of weeks ago, where we showed that starting off with these large-scale MOCVD grown MOS2, we could realize floating gate field effect transistors, which work in a similar way as the flash memories in our cell phones and consumer electronics. So here what we have is a floating gate in which, depending on the voltage configuration, we can store or remove charges from it. And then when you have a presence of these charges in the floating gate, it can influence your conductivity of your transistor. And what we realized during this work is that we can use these type of memory cells, obviously as memories, but we can also use them as just regular transistors. But what makes them better than regular transistors is that we can program their behavior. So we can program them to be always on, always off, somewhere in between. And then with this, we can realize circuits. This is one example of a basic circuit, which is composed of 4 of these floating gate elements. And depending on how you program these different transistors in the circuit, you can implement all the logic operations with 2 inputs. And this then makes it possible to make logic circuits based on memory elements, to also reconfigure them whenever you need them, to change the calculations you're performing. And this is one important step toward actually removing a very important limit in computing today, which is the von Neumann bottleneck, which separates the memory from the logic processing. And with this kind of approach, you can actually unify logic and memory together in a circuit and co-localize them. Now, in addition to this, we're also trying to grow large scale using commercial equipment. So this is an MOCVD commercial reactor from a company where we're trying to now implement growth of 2D materials on a wafer scale. And then the idea is that once we develop a reliable recipe, it will be possible to just buy the same equipment, reproduce it, and the growth of 2D materials will then stop being some kind of a black art that you have to develop always on your own in a laboratory, but you will be able to work with 2D materials in the same way as you work today with silicon or gallium arsenide or gallium nitride. You just get the material, you buy it, and you don't have to worry about its quality. It's always the same. Now, what I'm going to be talking about the rest of my presentation today was this work, as I mentioned, where we're trying to see what we can do beyond standard electronics. So it's pretty much accepted that 2D materials could be interesting for applications in standard electronics, but we would like to see how we could go beyond this and what are the other different ways of computation and data processing that we could implement that is based on some of the basic physical properties of 2D materials and 2D semiconductors. So in so-called traditional electronics, we're working with electrons and holes that can form charge currents moving through different devices, and then we manipulate these currents and measure voltages. And this is roughly some kind of a naive representation of what electronics comes down to. Now, one issue with this approach is that since your current is flowing through a conductor, it can also dissipate heat, and a lot of heat dissipation related to electronics actually comes down to the problem that you just have charge currents moving through a conductor and causing heating. Now, some alternative approaches that may go a little bit beyond this and allow you to address this problem of heating and current due to charge currents are, for example, spintronics, where the idea is that you encode information in the spin of charge carriers. For example, you could have spin down electrons moving in one direction, spin up electrons moving in the other direction, in opposite direction. And in this situation, we would have a charge current which would be equal to 0 because you would have electrons moving in both directions. So net charge current would be 0, but you would still be able to transmit information in the form of spin current, which would be non-zero. And then this could address some of this heat dissipation. It would, of course, introduce other forms of energy dissipation, but the idea is that this might be an alternative way of realizing computation in a solid state device and circuit. And then another similar approach would be based on encoding information into currents of excitons. So excitons are bound states of electrons and holes that can also move through semiconductors. I will also show you how they can be manipulated. And here again, the idea is that you would have an absence of charge currents because the excitons are electrically neutral. So maybe the heat dissipation and the energetics of the of computing and manipulating these currents would be different than in the case of just regular charge currents. And then finally, what is an additional scheme, alternative scheme to electronics that could be possible using 2D materials and semiconductors is the so-called Valleytronics, which is based on the basic physics and the band structure of 2D transition metal dichalcogenides, in which in the single layer limit of materials like MOS2 or tungsten diselenide, you have broken inversion symmetry, and you also have strong spin orbit coupling due to the large mass of constituent atoms. And this gives rise to this characteristic splitting of the valence band, which in the different corners of the Brillouin zone will have different signs. And then this makes these different corners or different points in K-space different. So you can have K and K prime points. And the idea is that you could encode information by confining charge carriers to only one of these points or valleys, or the other points and valley. And this could then work similarly to spintronics. And now the idea about this Valleytronics is that in 2D semiconductors, like MOS2, you have different things that come together in the same time, which allow you to realize this scheme maybe more easily than in other materials. And the first is that these valleys could be easily addressed optically. So if you look at these 2 points, I have here a more magnified view. You can address one or the other valley by shining circularly polarized light with right or left polarization. And then this would generate excitons inside the material. And when the excitons would recombine, they would emit again light with one or the other circular polarization, but this would be the same circular polarization as the light that came in if we have this valley polarization preserved. So by choosing the light polarization, we can select the valley. And this also, since we are talking about semiconductors here, we can also inject charge carriers which are polarized into the semiconductors using, for example, ferromagnetic electrodes. Again, read out optically, or we can read out using approaches from spintronics. And you can also modulate your Fermi level using external gate electrodes. So in the beginning, we thought that we could realize some kind of Valleytronics devices by looking at all these different possible combinations of inputs and outputs. So we can excite valleys using circularly polarized light or using spin injection, and then we can also read them out using light detection or spin detection. And we were trying to play along a lot with different types of devices using ferromagnetic electrodes, etc. But then we realized that the best and maybe the most efficient way to realize this type of devices is to use actually directly excitons and work and manipulate charges on the level of excitons and not on the level of at the level of single charges. So just a second. Single charges. So now, what are the excitons and how we can actually manipulate excitons inside the semiconductor material? So the excitons in semiconductors, they are formed when you excite them with light. So if you shine light on a semiconductor with energy which is above the band gap, then you're going to generate electrons and holes at the band edges. These can become free in the material, or they can form an exciton, which is a state where the electron and hole are attracted to each other. This exciton has a certain lifetime, and when this lifetime expires, then the electron and hole recombine, they annihilate each other, and you get light emission and light coming out of the material. And this is, for example, what you could have in standard photoluminescence. Now, in this type of just a standard exciton in a standard 2D semiconductor, unfortunately, has a lifetime which is too short, and it also is very difficult to electrically manipulated, but this all becomes easier and more possible using so-called interlayer excitons in transition metal dichalcogenides, especially their heterostructures. So the interlayer excitons were discovered and found when the first heterostructures were made, for example, using a combination of single-layer MOS2 and tungsten diselenide. In the case of 2D materials, this is very easy to do because the lack of dangling bonds on their surface means that we can take any one of those 500 or more 2D materials and put it on top of any other one of those materials. And when we do this, if we're talking about semiconductors, then we're also going to have, in certain combinations, different types of band alignment. And if we choose a combination of materials, like, for example, MOS2 and tungsten diselenide or MOSE2 tungsten diselenide, then we're going to have a so-called type 2 band alignment. And now when we shine light on a heterostructure with this kind of a band alignment, what's going to happen is that you're going to create excitons in one and the other material. These will be the so-called intralayer excitons. And these intralayer excitons, they will be broken up inside the material because this presence of the band alignment will create a built-in electric field. So it will be like we had a certain voltage applied across the material, and this will dissociate the exciton. So it will break it up. Then the individual charges will rearrange themselves in the heterostructure. The holes will go down in energy, the electrons up, so that they would minimize its energy. And what's going to happen is that you will have this very fast charge transfer where all the electrons will end up in one material, all the holes will end up in the other material. And then again, I have a bad network connection. It says, is everything okay on the other side?
It's okay.
It's okay.
It's okay.
It's
yeah,
okay. Good. Okay, no problem. Because I'm at work, I am supposed to have as good as it can be on my side. So, right. Then these single charge carriers, once they transfer to the different materials, they can again form an exciton and attract each other. But this now interlayer exciton will be composed of electron that is always in one material, hole which is always in the other. And this will give it a large lifetime. So the electrons and holes now, because they're found in different materials, it will take them longer to recombine. And what is also interesting is that now, since you always have positive charge in one layer, negative in the other, these excitons will also have a dipole electric moment. So you will be able to manipulate them using electric fields and voltages. And the creation of these excitons is very easy to observe using, for example, photoluminescence. So if you take a heterostructure of MOSE2 and tungsten diselenide, these would be the regular photoluminescence peaks of the individual materials. But if you make a nice heterostructure with a clean interface, then these peaks almost completely disappear. And you see on the lower energy, you see a new set of peaks which corresponds to this creation of interlayer excitons. And this pretty much happens because this process of breakup, dissociation, charge transfer, and creation of interlayer exciton is much faster than the normal lifetime of just the intralayer exciton in these heterostructures. So they break up, rearrange themselves before they can emit at the wavelength of the individual material. Now, this picture is also somewhat a little bit oversimplified because it corresponds to the situation we would have in, let's say, regular bulk semiconductors. In the case of 2D semiconductors, the fact that we can take any kind of a semiconductor and put it on top of any other semiconductor without respecting conditions like lattice matching also means that we now have additional degrees of freedom or complication in the transition metal dichalcogenide heterostructure. So what basically happens is that due to the presence of a lattice mismatch, your picture becomes a little bit more complicated. So yeah, there is a small possible lattice mismatch, which can generate this Moire superlattice in the 2D heterostructures. In addition to just the lattice mismatch, you can also have slight rotation. And the resulting Moire superlattice can dramatically influence the properties of the excitons and also how much they can move around in this heterostructure. So the first thing that they influence about the energetics of the excitons is that now, because we can have different lattices and also different relative orientations, if we take these two semiconductors on top of each other, then the transition between the electron in one layer and the hole in the other layer will involve points in the Brillouin zone which are no longer in the same position in K space, so they will not be spatially direct because the charge carriers are in different layers, but they will also be momentum indirect because there is no way to actually put them in the same place in the K space. So to go, for example, to recombine a hole in tungsten diselenide or an electron in tungsten diselenide with the opposite charge in MOS2, you would actually have to change also a little bit the momentum of the charge carriers. And this then explains why the interlayer excitons occur at the energy at which they occur. So if you just looked at the band structure of a heterostructure composed of molybdenum disulfide and tungsten diselenide, then this would be the energy which would correspond to the direct K to K transition. But in this system, we actually have at room temperature or more than cryogenic temperatures, we have the possibility of also these momentum indirect transitions between the gamma point in tungsten diselenide and the K point in MOS2. And then if you look at the energy difference, then it's pretty much going to correspond to what we see in photoluminescence. So we see roughly these energy peaks in photoluminescence around 1.5 or a little bit more electron volts, which can be explained by this energy difference between the gamma and the K point. So this means that the dynamics of excitons is a little bit more tricky to understand than what you would usually expect from just a simple picture of band alignment. And to get these excitons to show up, as I mentioned before, it's very important to create these high quality heterostructures. We use one of and actually several different variations of these transfer methods that have been very much popularized in the research community. So we exfoliate one material on a substrate, and then using some kind of a sacrificial polymer, we can remove it and transfer and build a heterostructure on a target substrate. Now, what is important for seeing these interlayer excitons is that you need to make very nice, very clean, high quality heterostructures, and it's important to anneal them properly so that once you start off with something relatively dirty with a lot of residue, you can end up with a clean interface in the end. And then when you make your final heterostructure, which for the highest optical quality has to be also encapsulated in boron nitride, there are all this annealing and different cleaning procedures and a lot of practice. You can end up with these very, very clean interfaces where you can actually observe the interlayer excitons. And this kind of heterostructures we build using some kind of a motorized home-built setup where we have control over a lot of degrees of freedom, rotation, translation. So these are all standard TOLABS translation and rotation stages under an optical microscope, and it also helps to put everything into a glove box because then you don't have to worry so much about humidity and oxygen. And once you build such a heterostructure, then it's also important to confirm the relative orientation between the different layers. So this we can do, for example, using second harmonic generation and the polarization dependence, and then we can measure what is the relative orientation between the different fields, because the relative orientation is going to influence a lot the probability of transition between the different K points in the different materials, and also the landscape for the Moiré potential that can influence the motion of excitons. And then finally, once you have these nice heterostructures, you can look at photoluminescence, and then you can see how once you have a heterostructure, your photoluminescence peak goes down in energy, and the intralayer exciton peaks are suppressed, and this then tells you that you have a good and highly efficient formation of interlayer excitons inside your structure. Now, once we have these excitons in the materials, how can we manipulate them electrically, and how do you know that the excitons are moving and doing something? So the easiest experiment that you can do is that you can just shine a laser laser light onto your heterostructure, and you can record the shape of the excitation spot under a microscope and a camera. And then you can easily see that as you change the power of the excitation, this spot is going to change in diameter. And this is what's happening here, for example. So here the spot is being shining on the heterostructure at the corner, and then you get this spreading of the emission. So it's normalized in intensity, but you see that the cloud is sort of spreading out from the point at which we inject the excitons. So why is this happening? So what's happening is that we inject excitons under the laser beam. They can diffuse a certain distance away from the injection point, and once their lifetime is reached, they emit light. Now, the driving force for this emission, this diffusion of excitons, is the temperature gradient. Since we have a laser, we're slightly heating the sample under the laser beam, so there the temperature is hotter, and the excitons are flowing to the colder regions. And the excitons, since there are also electrical dipoles, they are slightly, there is an electrostatic interaction which is repelling them. So they kind of squeeze them in one place. They would like to spread out to minimize the electrostatic interaction. So that gives rise to a chemical potential gradient, and the excitons would like to diffuse again away from the injection spot to minimize their energy. So these are the driving forces. And now, since the excitons have an electrical dipole moment, we can also change their energy by applying a vertical electric field. So this is the energy of the exciton or its modulation, the value of the dipole, and the application of an electric field in the z direction can change the energy of the exciton, which is diffusing in this heterostructure. And with this electric field, then we can establish control over the diffusions. We can introduce an electrostatic potential, some kind of a potential dip or a potential barrier. And this way we can switch the diffusion of excitons in the same way you could switch the motion of charge carriers in a regular semiconductor. And here on this series of images, which correspond to actual data, you can see in the top a map of the exciton cloud and how it's spreading out as you're changing the intensity. It's also here reaching this region of the device where we apply an electric voltage. And what happens is that you see as the cloud reaches this potential dip, it somehow gets attracted into it. And in this second map, we see an energy of the exciton cloud recorded in the same time. So there is a trick with prisms where you can basically take a strip in space of the exciton emission image, and then you can feed that emission to a spectrometer and record the energy. And then here we can see the two clouds. So the first upper energy cloud corresponds to the portion of the exciton cloud which is free. It's not in the trap. And then once a part of the cloud reaches the trap, the energy goes down because the excitons fall into this trap with the lower potential energy. And with this, we can now realize simple transistors and switches, which work on excitons and manipulating currents of excitons and not manipulating currents of single charge carriers. Now, this idea has been around already for quite some time. So the first reports of so-called excitonic devices and transistors actually go back to 2001, but in those days, they were realized using 3-5 semiconductors grown using MBE and into heterostructures. And the problem was that due to the relatively low binding energy of excitons, these type of devices could not work at elevated temperatures. So the highest temperatures for the operation of excitonic devices was on the order of 100, maybe 150 Kelvin. But in 2D materials, excitons have a much higher binding energy, so they are much more strongly the electrons and holes are much more strongly attracted to each other, and it is possible to make transistors which work with excitons, but that can be operated at room temperatures. And this was the example that we had here. So using this approach of manipulating the exciton energy using vertical electric fields, we could, in a heterostructure, we could switch on and off the current of excitons, and this you can see by looking at the emission coming from this spot at the heterostructure. So in this device, then we had excitons which were generated using a laser beam. They created the current and gave rise to light emission, which we could then modulate using electrical voltage. And we could also record a switching curve, which is in every way analogous to switching curve of a transistor, and we could have even an on and off excitonic current ratio. And we could not only switch the excitons, but we could also change a little bit modulate a little bit their current. So by introducing a series of electrodes with a series of voltages, you could create something that looks like steps going down for excitons in energy or steps going up. And then this worked in a similar way as a diffusion, as a drift force for charge carriers in semiconductors. So it sort of mimicked the idea of having a potential and of modulating the current by introducing some kind of an effective potential. And with these steps, we could then enhance the current of excitons. They could diffuse further, or they could diffuse shorter distances, and this kind of mimics the action of forward or backward bias in a standard semiconductor device. But now at this point, we thought, okay, this is all very nice, but we would also like to somehow introduce this polarization and the Valley physics and the Valleytronics into these devices. And we couldn't do that using this combination of materials because this transition was between the gamma and the K point. And in the gamma point, we cannot have Valley polarization. So the light which was coming out of the device couldn't be polarized. And to go around this problem, we switched molybdenum disulfide for molybdenum diselenide. So we made the next improvement in devices. And in this type of devices, we could indeed observe polarization. And more interestingly, we could actually switch it using a local electric gates. But what happened is that the excitons got trapped. So the Moire potential in these materials, this combination of materials was so strong that the excitons could no longer freely diffuse. They were trapped in different regions of the Moire lattice. And I'm going to go to that point in a few slides. So when we made these high quality heterostructures, we saw this very nice interlayer exciton emission and the two characteristic peaks, which are separated by something like 25 millielectron volts. And we attributed these two split peaks in the interlayer emission to the observation of transitions between the top of the valence band in tungsten diselenide and the bottom of the conduction band. So this is the standard spin triplet transition, which gives rise to emission with the same polarization. But in addition to this, we also had the higher energy peak, which was weaker, but it was still there, which we attributed to the transition between the valence band and the next subband in MOSE2. And this subband is there because due to the spin orbit coupling, in addition to the strong splitting in the valence band, you also have a smaller splitting in the conduction band, which is the same order of magnitude. So it's 10 to 20 millielectron volts. So in heterostructures, can actually see these both transitions. In single materials, they're not there. So now what happens when you shine circular polarized light on these heterostructures? So in a monolayer, when you shine a circular polarized light on a isolated 2D material like tungsten disulfide, I said that the polarization of the light selects one or the other value. And then you get the emission of light. If you have good polarization, you get the emission of light at the same polarization as the light that you use for excitation. In heterostructures, you actually have a more complicated picture. So with the circularly polarized light that you shine on the structure, you select a certain valley. But now in this valley, in the heterostructure, you can have both spin triplet and singlet transitions, and these will then give rise to emission of light with different polarizations. And you can actually change electrically which polarizations you're getting and which regions of the heterostructure are active. Now, to observe these two peaks, it was important to encapsulate the materials into boron nitride. So this was the first example of interlayer exciton observed in these heterostructures, but in that case, they were not using encapsulation, so they were not able to actually resolve the finer features in the spectra. But with the boron nitride encapsulation, we could really resolve these two peaks, which corresponded to these singlet and triplet transitions. And now in this device, since we are talking about the device, we also can apply electric fields and change the doping levels, and this can then tune the light emission coming from this excitonic device. So by applying a vertical electric field, we can change the energy of the electric dipole and the energy of the exciton, and this corresponds to just a simple Stark effect. That's the polarization times electric dipole times electric field gives you the change in energy. So as we change the electric field, we can change and tune the transition and the energy of these excitons, and then they emit at different energies because we change their energy using the electric field. But if we also allow the charge carriers to go in and out of the heterostructure, then we can in the same time also dope. And this doping is interesting because now, in addition to just changing the energy, we can also change the polarization of the light that's coming out of the device. And so for strong electron doping, we can have these two transitions which correspond to the same excitation and the opposite polarization. But then for hole doping, we actually switch to a regime where this excitation becomes oppositely polarized, the emission becomes oppositely polarized to the excitation, and the other peak becomes linearly polarized, so we can no longer resolve it by using circular polarization. So the way we explain these results is that what we think is happening is that in this Mare superlattice between the two materials, one group of Wang Yao from Hong Kong has predicted that we're going to have different types of selection rules depending on which region of the Mare lattice is optically active. So depending on the local symmetry, different portions of the Mare superlattice will have different selection rules. They will, in the same valley, these two transitions will emit with different polarizations. So one region is going to emit with what we see, which corresponds to the interlayer separation. Again, if you put boron nitride in between, we get a larger size of the dipole, which is consistent, and it tells us that we indeed have here a single layer of boron nitride. And now the excitons, since the Mare potential is weaker, are free to move, so they can now diffuse, just like in the beginning. But since the optical transitions are direct or more direct in K-space, they also preserve polarization. So now when we shine circularly polarized laser, we create excitons which are composed of spin up electrons and holes, and they diffuse. But this diffusion is now also a diffusion of spin polarized excitons. So we have combined both the exciton current control and the exciton spin control in one type of a device, which was actually a huge step forward, because now we have a Valleytronic device, except that it works with excitons and not with single charge carriers. So with this, we can then record we can manipulate the currents, as we said, and we can directly record the energy of these exciton clouds. So we can introduce a potential barrier that blocks the diffusion of excitons, and we can create a potential dip that's going to cause these excitons to fall in and lower their energy. And all of this is spin polarized. So all these currents and motion of excitons is spin polarized, is also valid for spin polarized excitons. Now, the other thing that is interesting here is that we can use this potential arrangement to also trap and try to squeeze excitons in one place. So using this arrangement of electrodes and voltages, we can either push them out of a region, or we can confine them into a region. And then when we confine them, by looking at the energy difference between the free excitons and the confined excitons, we can actually estimate the density of excitons in this structure. And the way we can estimate the density of excitons is that if you squeeze the excitons in one place because they're electrical dipoles, squeezing them costs energy because they would like to repel each other. So the difference between these two voltages, even though the voltages are the same in magnitude, but they're opposite in signs, you're going to create different energy shifts. And the difference in these two energy shifts actually tells us how many excitons we managed to confine in this region. And from this, we can see that we can actually increase the initial exciton density by a factor of 10. And this then motivates to do further research and try to introduce things like Bose-Einstein condensation of excitons in this type of structures, and see if we can maybe introduce some kind of a coherent state of excitons in a solid state device based on a 2D heterostructure. So at this point, I would just like to summarize, since we're running out of time. So I showed you the demonstration of a first room temperature exciton transistor based on 2D materials, how we also can manipulate exciton energies and polarizations in a Moire superlattice, and finally how we realized valley polarized exciton currents in a heterostructure where we managed to decrease this Moire coupling. I would like to, of course, thank my group for their very hard work. This is a photo of us in the lab. So some people have left, some new people have joined. But the group members who did most of the work that I presented today were Alberto Cherokee, Dmitry Unuchek, and Ahmet Afshar. And the other group members are also doing very interesting things, but that maybe I'm going to talk about later. I would also like to thank collaborators, funding agencies, and of course all of you for your attention. So I would like to answer questions if there are maybe any questions from the audience.
Hi, Professor Kiss. Thanks for your wonderful talk. Yeah.
Thank you very much.
And our staff, I will collect here several questions from different live platforms, for example, YouTube, Facebook, and the Bilibili website for you to answer. And I will ask the questions on behalf of the audience. Thank you. The first question is, so 2D heterostructure samples in your work, are mainly prepared by mechanical exfoliation method. So have we tried the other CVD method to make the samples and then compare the difference by different methods?
Yes, we are working on this. So far we haven't in my lab made a structure with interlayer excitons, but there is one person in the lab whose project is only to do this. There were other groups in world China who actually showed that this is possible. So with the CVD material, you can also realize heterostructures and see the interlayer excitons, and they have good quality. It was just that in the beginning, since it takes a lot of time to make these devices, the people were maybe just a little bit more conservative and wanted to make sure that they use the highest quality materials. But in principle, this should also be possible using CVD grown materials or MOCVD grown materials.
Okay, thanks for your response. And the second question is for MS2, WS2, WSE2, 2D heterostructures you mentioned. So what's the effect of layer thickness on the interlayers, excitons or in modular lattice? Yeah.
Well, basically everything we do here is with single layers, because if you change the thickness of the semiconductors, they no longer are direct bandgap semiconductors, and then you cannot really do this interlayer exciton physics so nicely, because you just can't create the excitons in the first place. So maybe you can do some other interesting electrical transport related phenomena, but not so much optics.
Okay, thanks for your detailed response. Another new question from the audience. Just you mentioned in the beginning, I think he or she want to know the effect of lateral sides of these 2D materials on the properties, for example, magnetism, for example.
Well, the lateral, we haven't really looked so much. What people are normally looking for is the vertical, the thickness. So the thickness is the most important parameter for tuning. And then laterally, you would have pretty much just some normal quantum confinement. From 2D, you go to 1D. So if you take a semiconductor, a 2D semiconductor, then the vertical thickness will change how the nature and the band structure from indirect band gap to direct band gap, and also the size. But then when you go into 1D confinement, then you're probably going to raise a little bit the band gap with the extra confinement, but you're not going to change so much the nature of the material.
Okay, thank you.
And yes.
Okay, thank you. So the third question from the audience. So what's the challenge and perspective of the external devices based on the 2D semiconductor heterostructures? Thank you.
Well, the challenge is really, we would like to, of course, also go away from these exfoliated films, because the devices are simply, it takes too much time to make them. Every one of these devices that I've shown you, to make the original device, it took maybe 1 month when everything was working, and sometimes things don't work. So then, it can take much more time. So obviously this is slow for research, and it can also be sometimes demotivating for students when they work a long time and the device finally doesn't work. So we would like to scale up the production and the fabrication. And of course, the big challenge there is to start using the synthetic materials and some kind of a fabrication approach which is less manual, so more automated.
Okay, thank you. And last question from the audience. Just you mentioned all the heterostructures, 2D heterostructures, but they just vertical heterostructures. So have we tried to construct lateral heterostructures for the external devices?
No, not really, because that also again depends on growth. So for that you really need to have a high quality grown material. And with the lateral, it's a bit. With the vertical, the nice thing is that you can very easily modulate their energies using some kind of gates. But with the lateral, I have to think about how that could be actually done.
Okay. Hi, Professor Keith. Thanks for response to all questions. From the audience. And thanks again for your time. And also welcome to submit your work to SmartMat. Yeah.
Thank you. Thank you.
The first issue for SmartMat will come out in the middle of this month. After 1 week, I think. Thank you.
Well, congratulations and good luck with the submissions.
Thanks for your support to SmartMat academic seminars. Thank you.
Thank you. Thank you. So do we have how do we continue? Is this,
Oh, that's finished, for the talk.
Okay, finished. Thank you then.
Bye. Okay.
Thank you. Bye. Have a nice evening.
Nice talk.
Bye. Have a nice evening.
Bye.